It's like
they have the same shape and their corresponding linear measures are proportional.
Hold up, stop. One at a time.
I got it.
Go ahead.
Okay, so they can be like almost the same thing, like the same shape, but like different sizes.
Perfect.
Oh, I got
Perfect explanation right there.
They're the same shape and their corresponding linear
So,
measures.
because of what Alex just said, when we talk about similar solids, can I talk about similar anything? Yes. Right? So today we're going to concentrate on similar solids, which means the things that we've been talking about, prisms, cylinders, and that kind of stuff. But I can do this with any shape, really, okay? And what Alex came up with was that they're the same what? Shape. But different sizes. So when we do this in geometry, we bring up, and I can't say it, I can't say the word, but there's a Russian doll, begins with an M, I can't say it, Marushka or something like that. Oh yeah, there it is, up there. Have you ever seen this doll where you open up the doll and there's another doll exactly like that inside it?
No, it's the they're usually made of like wood and
Yeah. Okay, so that's an example of something being a similar solid. So if this is true, if it's the same shape but different sizes, what does that mean? What do they have in common?
They have the same like angles.
Proportional.
They have the same what?
Angles.
Perfect. So if they're the same shape and the same but different sizes, all the angles are exactly the same?
Yeah.
Yes. So we would say that instead of saying they're the same, we would say they're what?
congruent.
Congruent. We're trying to be professional here. So all angles are congruent. Okay? So here's the question. Don't say this out loud. If I have a sphere, everybody know what a sphere is?
Oh, sphere.
Why didn't we do sphere?
I thought you said sphere.
We did spheres.
We did?
Yeah, it's like a circle.
We found the volume.
A snowball.
We had to do that in our
We did a volume, didn't
We
we?
did that there.
Yeah, it was on our last time.
Snowball.
We did yesterday.
We didn't talk about the surface area of the sphere.
That is not
But
nice.
But it gave us a
They
formula.
did.
Okay.
It was.
Anyway, so here's a question. Would you consider all spheres similar to each other?
Yes.
You're supposed to think.
Oh,
I didn't hear you say that.
Yes.
well, I can't.
I heard him.
So would you say it is?
Yes.
Or are they all congruent?
No, because one could be smaller.
Because they don't have an angle.
Right? So when we talk about congruency, if something is congruent to something else, it's what?
Exactly the same. Like same
It's the
shape,
exact
same
same thing,
size.
right?
So they don't be fixes.
So basically, if we had a women's basketball and we ordered it from the same company, we would expect that second women's basketball to be the exact same thing, right? They would be congruent. So here's the question. Are congruent things similar?
Yes. No.
Yeah.
No.
No.
Yes, right? They're still the same shape and they're actually the same size, so they are similar to each other too.
But how? Because it says different size for the surrounding scene.
Well, yeah, but if it's the exact same of everything, it's got to be the exact same, right? So they got to be similar to each other. Similar is just being like more complex, I guess. You know what I'm saying there?
Complex, like
My brain.
All right, so what is true then about the different sizes? So if we took a box, okay, and our box, we're going to clean this box.
Back there.
All right. Alex has a Kleenex box over there, and Addie goes and gets one of those brown boxes right over there in the corner, okay? And just for argument's sake, we're going to say that those are similar boxes to each other. All right? Obviously, all of the angles are the same because it's a box, so they're all 90-degree angles, right? So what makes them different?
The lengths and
The size.
The sides, right? The lengths of the sides. Okay? But is there a relationship between the side on that and the side on that if we say that they're similar to each other?
Yes.
There is? And what is that relationship?
They both have.
No, the relationship of the lengths of the sides.
Oh, okay. No, thanks.
So, how do we just say that they're different sizes? Or how do we compare them? How do we know that they're similar to each other?
Back to back.
We just say, well, because they look like?
No, because you did.
So would you say definitely that that box right there that Alex is holding and that box back there in the corner is
They have to.
similar to each other?
They have to be the same 3D shape.
Okay. Wait. Hold on. Do you understand what I'm trying to get you to think about? Yeah. There's got to be some kind of relationship. Because all the angles are congruent, you told me. So it doesn't matter how big the box is and how small it is. If they're similar, all the angles are exactly the same.
Would they have this? Would they all have to have the same sides? Amount of sides?
Okay, they'd have to have the same amount of sides because they have to go together exactly, right? So that box has to be compared to that box. I can't take a box and compare it to a pyramid.
Nope.
Agreed? Because they're definitely different shapes. Okay? So there's got to be something that is a relationship with the lengths of the sides. Either if I'm thinking about going up and down or if I'm thinking about going left and right. And so maybe a word that we need to talk about are corresponding parts. We talked about this before, I believe. But what does the word corresponding mean?
They work together.
Go together.
They go together, I like. Okay? So the corresponding parts would be edges, or if you want to think about lines, I guess, line segments that are in the same spot. So when I'm comparing two boxes, I'm talking about the long side of the box, or the short side of the box, or the height of the box. You understand what I'm saying? So when I'm talking about this right here, and then I get a bigger box in the corner, the corresponding part has to be that I'm looking at the box in the same orientation. Meaning, Carson's seeing it in a different orientation than Aurora would right now, right? Because Carson would first see this side right over here, but he would understand that it's in an entire box. Aurora's going to basically see the box from the front. Nobody really sees the bottom unless you lay on the floor, right? But if Aurora is going to compare this box to that box over there, she's going to look at the front face. She would have to look at the front face over there, and there's got to be a relationship between those two faces, okay? Does everybody understand what I'm getting at? Yes. Okay, so what do you call that? Any idea?
Corresponding boxes.
Probably not. This is probably something that you've never really thought about. So we're going to compare something called, or we're going to compare ratios. What's that mean? Fractions, okay? Now, in these ratios, when we're talking about similar solids, we're going to get more in depth and we're going to call the ratios a scale factor. And a lot of the times, a scale factor is represented by the small letter K or the lower case K. Don't ask me why. And I'm not just making it up because K's are cool. Yeah, you're a K too, so you should think we're cool.
K's are cool.
You
spell cool K-O-O-L.
I know. Okay. So we're going to make a comparison using ratios. What's a comparison making using ratios called?
What?
What's a comparison of ratios?
Oh. A proportion.
A proportion. We're going to set up proportions and try to see if they are correct. But more importantly, we're basically just going to compare ratios. And so this scale factor has to be the exact same for every set of corresponding sides or edges. So again, what does corresponding mean again? It means that they're in the exact same spot. So I'm going to make that comparison looking at the exact same thing. Now when you set up this fraction, right? That's all a ratio is. I'm going to set up a fraction. I always want to be consistent. So I need to compare the big side compared to, when I say the big, I'm talking about the shape. Okay, so I'm talking about that big box to the small side. And it has to be a corresponding side. And then every time that I do another one, I have to do the same order. So the big one's always going to be on top. The side, maybe this is, we would call this side 1. And then I'm going to compare side 2 to side 2. And so on and so forth. So what I'm trying to get you to realize is that the big sides always have to be on the top, and the small sides always have to be on the bottom. Now, if you want to put the small sides on the top, that's totally fine, but I'd have to take all of my fractions and flip them over. So then I would have all of the small ones on top and all the big ones on the bottom. So all the things that you're comparing have to be from the same exact shape in the same exact spot. That make sense? And this is called finding my scale factor. And if all of these are the same, then your scale factor is whatever that fraction is in lowest terms. So I'm going to reduce that fraction. Now, if they give you 3 sets of things, and you go through and you compare the first 2 to the second 2, and they're the exact same, you reduce them, you get 1/2 is equal to 1/2. You cannot just stop right there if they give you another set of numbers to compare. You have to check all the things that they possibly give you. That makes sense what I'm saying? Okay? So, again, this is a little harder to kind of draw. So, turn your book to page. Here we are, 586. So, on page 586, the first part of this is looking at number 3. So, in number 3, again, make sure that you read the directions. In number 3, it says, determine if each of these pairs of solids are similar to each other. Okay, so do you see what I'm talking about with similar or corresponding segments, corresponding parts, corresponding edges, however you want to think about it in your head? These are pretty easy because why? They draw the, like in number 3, the 2 boxes in the same, what I call orientation. You know what I'm saying there? Okay, when it gets confusing is if they would have taken that big one and like rotated it this way. And they would have set the big one this way and then the small one this way. That's when you got to really take your time to match up the numbers that are in the corresponding spots. Everybody on the same page with me here? Okay, so what is one fraction that I can make with corresponding sides? So look at the same spot in the little one to the big one, and what's a fraction that I can make? 1/4 or 4/1. Okay. Mr. Kolbeck said 4/1. So if he does 4/1, he has to do the big one to the small one every single time. So where was your 4/1 from? How would you describe where you got those numbers?
The left side.
The left side. Okay, everybody see the ones that he's looking at? Okay, so now Grace is going to say what? 8/3. So we set this equal to each other because we're comparing them, right? So basically, remember, we got to do the big one to the small one, so she did 8/3. Is 4/1 equal to 8/3?
No.
So as soon as you get a no, the whole thing is no. They are not similar to each other. That makes sense? If this one was yes, then we would have had to do the third one. What would the third side been? 4/1 again, right? So again, notice 4/1, 4/1. If those would have been the first 2 that you did, yes, it's a yes that those 2 are similar to each other. You cannot stop if they give you 3 sets of them. Because obviously, if you would have stopped right there, you would have said yes, but the actual answer was no. That makes Make sense? Okay? And then if all of them are the same, then we'd say yes. And if they ask you what the scale factor is, then it's that number. So basically, here's the question. Just think about this again. Don't say anything out loud. How many scale factors does each similar solids or similar shapes have? How many would you say?
3.
Why 3?
Because the height, base,
Okay, good thought, good thought. But as soon as I compare the heights, I'm comparing the heights to the weights, or the widths, and the widths to the lengths. Okay? Why do you say 12? Okay, that's how many sides there are. That's another great thought. Still wrong.
1.
1. Why?
Because if you divide them, it should be the same decimal number.
Okay, I can live with that. That's getting closer. Still kind of wrong.
2.
Why 2?
Because I don't know how to explain it.
Unfortunately, she's right, but she doesn't know how to explain it.
Like spheres have something to measure. Spheres and cylinders only have 2 measurements: the side and like the top.
Not true, but for our argument, maybe you could say that. Okay?
Could it be because you need 2 to at least make like more than 1 fraction?
2 because they.
Let's go to number 4, and I'll show you how we can say this. In number 4, tell me one ratio that you would form. 6/4. Okay, so we're doing what to what again? Big one to small one, right?
3 to 2.
So the next one has to be 3 to 2. Are those equal to each other?
Yes.
Yes. Okay? So our answer is yes, and they don't ask this for you, but what is the scale factor? The scale factor is whatever you have as your smallest fraction. So my scale factor is 3/2. So how can I get another scale factor for this problem? If I'm telling you the answer is 3/2, how can I get another scale factor
Add them together.
that basically says the exact same thing? Why?
Reciprocal.
Exactly right. So remember when we said you had to be consistent and do the big to the small and big to the small? Well, what happens if Aurora said, I want to do the small to the big from the beginning? If she does that, she just flips the other one over, and don't I get the same thing? This is still yes. But now when I reduce, my answer is 2/3. But notice what are they? They're basically the same thing. They just did what to them? Flipped them around. So this is how you always get 2 answers. It depends on if you're doing the big to the small or the small to the big. That makes sense? And that's how you always get 2 of them. It's basically going to be the same fraction. You just flip it over. So if you get 3/2, you say, yes, that is true. My one scale factor is 3/2. The other one is 2/3. This one over here, if this would have worked and we would have had 4/1, what would my other one been? What do I do to 4/1? 1/4. I just flip it over. Okay? But because this one had 8/3, it didn't work out. See what I'm saying? So it's just depending on if you go from the big to the small or the small to the big. So another thing that you can think about, if I go the big to the small, my scale factor is always going to be bigger than what? 1. If I go small to big, my scale factor should always be a what? A fraction or a decimal. Exactly right. So again, that's probably way more advanced than we probably have to be for this section, but we're just showing you some of those things.
Is there ever a time where it's different? Like,
If they're different, then they're not similar.
no, I mean, when the answer for the scale factor is different. Like, if you go, like for the 2 answers, they're not the same fraction.
No. They're not similar altogether. I can never, like right here, you might look at that and say, well, those are 2 different, but if I reduce this, I get the exact same thing. So if they are different and I can't reduce them to get to the same, so essentially if I punch it into my calculator and I get 2 different decimals, that automatically says the whole thing's no, and they're not similar to each other.
That's not that's
Okay, so what are you asking?
like if you flip it over, will you ever get a different instead of using that one again, would you ever do it before?
No. Different numbers, you're saying. So if I can't flip 3 halves and get something besides 2/3.
Mm-hmm. And then, what if there was a smaller fraction that if it was flipped over?
It's not going to ever happen that way because then this wouldn't ever be equal in itself. The numbers that you would have to make this fraction wouldn't work either. Then the numbers have to be essentially the exact same, they're just flip-flopped. I can't have totally different numbers here from here and expect it to still be similar to itself. That makes sense what I'm saying? You can try to do your new math over and over again, but it's still not going to work. Trust me. Okay? So look at number 5 and number 6 then. In number 5 it says, find the missing measures for each pair of similar solids. So they're already telling you that the solids are similar. Okay? So when they ask you to do this, all you are doing is setting up your proportion. Okay? So in number 5, what would be my ratio for the radii? 45 to 6. Everybody good with that? Yeah. So because Grace did it 45 to 6, my second fraction has to be what?
250 over x.
250 over x. And now, remember how to solve the proportion?
6 times 250 divided by 45.
6 times 250 divided by 45. Somebody punch it in your calculator.
I don't have
Jacob?
6 times 250. Wait, that's 1.
33.33 repeating.
So let's do it this way. So the last thing I would look, does it make sense? If the top number is bigger than the bottom number on this one, the top number better be bigger than the bottom number on this one. Okay? So try number 6 by yourself. Set it up. Notice here, in number 6, they ask you to do 2 different problems. To find x and to find y. So you're going to have to set up 2 different proportions. Now, basically, when I set up this like this, I'm just showing that I'm going to do this proportion first, and then I'm going to use that scale factor that they gave me of both numbers, and I'm going to use that and do the y part second.
Oh, I did the wrong one. I did part of that homework.
If I write it out like this, where I'm showing you all 3 of them at the beginning, I'm going to do it in 2 different problems. The first one's going to involve this middle fraction with my x. The second one's going to have that middle fraction with the y. Okay? So, what'd you come up with for x?
That is not.
Yeah, I got 50.
How much?
50.
50.
50.
Okay? How much for y?
36.
36. So, again, adding with your first number, when you gave 100, I knew it wasn't right just because, see how the bottom number should have been bigger than the top number? So you see what you did wrong, kiddo? Okay.
I did 815 on accident.
Great job.
I know, and I got the answer though.
How do you know?
Because
Did you cheat?
No, because it's easy, because it's 15 over 5.
Awesome. You're a genius.
Where's he getting 15?
He did the wrong problem.
I did 15.
Last thing. Last thing. Everybody good with this? Both of those fractions? Or sorry, proportions? Okay now? The last thing, if you start doing this with story problems and such, or even in problems here where they give you the figures, what's the most important part before you even start? What? Exactly right. See if they have or give you the same label. So make sure centimeters to centimeters to centimeters to centimeters. Again, if they give you a different label, then the first thing you have to do is convert it into that other label. Okay? Make sense? Questions here? Anybody? All right, so let's do some problems. I think this is the last section.
There's one more.
And,
Oh. I thought you were counting this one too.
No. No, there's only one.
so we're not going to do the next section.
Oh. Okay.
Will we review the semester with you?
On Monday.
Well, what are we gonna do then on Friday? I mean,
We're gonna do a test.
Well, this is where we need to kind of talk about.